Hello friends, welcome back. In previous video, we have seen what are the anomeric effect and the mutarotation. In this lecture, we are come across the size determination in the carbohydrate or a sugar unit. So let's see the determination of ring size. Suppose we have a carbohydrate and we want to know the actual ring size or a number of carbon in this sugar unit. Then in a practically how we can determine the actual ring size of the sugar. So, the anomeric carbon can be found via the methylation of the OH group followed by the hydrolysis. That means we have a sugar unit and in this sugar there is an anomeric carbon and this anomeric carbon can be found via the methylation. That means in first step we do the methylation of this given sugar. That means we have a sugar. When it is reacted with the excess of methyl iodide and the silver oxide, then after the reaction, the all OH group or a hydroxyl group in the given sugar can be converted into OCH3. That means there is a methylation of this sugar can be done when it is reacted with the methyl iodide, excess of methyl iodide in presence of silver oxide. Okay, in first step there is a methylation can be done. Okay, in next step there is a hydrolysis by using the HCl and H2O, and after the hydrolysis this anomeric OCH3 can be converted into OH group. That means there is a formation of hemiacetal molecule. Okay, that means this pyrano structure is in a equilibrium with the open chain form. That means this ring can be converted into the open chain form and this open chain form can be converted into this ring. Okay, so from the open chain form we can determine the size of the ring because the anomeric carbon attached OH group is the one that form the cyclic hemiacetal. So from that we can determine whether it is a 5-member sugar or a 6-member sugar. So let's see the reaction. Here you can see one sugar unit and this sugar in first step we do the methylation, okay, by using excess of methyl iodide in presence of silver oxide. Okay, so after the methylation these all hydroxyl group get converted into this OCH3 and this is called the acetal because this anomeric carbon is attached to one OCH3 and this O and this ring. Therefore this is called the acetal. In first step we do the methylation of this sugar and we got acetal as a product. In next step there is a hydrolysis. After the hydrolysis this OCH3 of this anomeric carbon is converted into OH group and this structure is called the hemiacetal. Why it is called hemiacetal? Because this anomeric carbon is attached to one OH group and one OR group. Therefore it is called the hemiacetal. Okay, and this is present in the equilibrium. Therefore this converted into open chain form and this open chain converted into this ring form. So from the open chain form we can determine the ring size from this anomeric carbon. Here it is a OH group and from this we can determine this is the 6-member cyclic sugar. So we can determine the ring size, determine the size of this carbohydrate from this reaction. There is a one more method. A monosaccharide's ring size can be determined by the oxidation of an acetal of a monosaccharide with excess of periodic acid. The products obtained from periodic cleavage of a 6-membered ring acetal are different from those obtained from the cleavage of the 5-membered ring acetal. That means the given sugar can be reacted with the excess of periodic acid and after the reaction of periodic acid we got the product and the products are different from the 6-member sugar we got the product and from the 5-member sugar we got the another product. That means 6-member sugar gives different and 5-member sugar gives different product. So from that we can determine whether it is a 5-member or a 6-member sugar. So see the reaction. Here we have a carbohydrate or this sugar molecule, and when it is reacted with two equivalents of periodic acid. So what is the function of this periodic acid? When we react this periodic acid with this sugar molecule, here you can see these two OH group, okay, and here another one OH group. That means these two OH groups are the syn to each other. Therefore, when we reacted this molecule with the HiO4, there is a cleavage of this bond, okay, and here again there are the two OH groups, therefore there is a cleavage of this bond. That means when we reacted this sugar with the HiO4, here you can see three OH groups, okay, and two bonds will be break, hence we write here the two equivalents of HiO4. And when we react this HiO4 with this sugar molecule, there is a cleavage of this bond, and after the cleavage, okay, after the cleavage, this carbon atom is joined to one more OH group when it is reacted with this HiO4. That means after the breakage of this bond, this carbon atom initially this is attached to this OH group, this ring, and here it is a one hydrogen, okay, but after the cleavage of this bond, this carbon atom attached to one more OH group. That means initially here it is only one OH group. After the cleavage with the HiO4, there is one more OH group is attached to this carbon. That means in final step, this carbon atom containing two OH group, one hydrogen, and remaining this ring, okay, and here this bond also break. Therefore this carbon atom initially you can see this carbon atom is attached to this OH, here it is one hydrogen and this is the ring, okay, but after the cleavage of this bond and this bond, that means here it is a breakage of two bonds, therefore two OH group can be attached to this carbon. So finally this carbon is attached to three OH group. These two OH group, after the cleavage of this bond, there are two OH group attached to this carbon, and here it is already present one OH group. That means this carbon contains three OH group and one hydrogen. So this is possible structure? No. So therefore after the removal of this water molecule, we got the formic acid as a product, okay. So in this step we got the formic acid from this carbon, from this moiety we got a formic acid as a product, and from this remaining moiety, here you can see after the breakage of this bond, this carbon atom attached to another OH group. That means here two OH group are present after the breakage, okay, that means two OH group, one hydrogen, and remaining ring. So after the removal of this OH, there is a formation of two aldehydic molecule. That means from here we got a one aldehyde, and from here on this carbon atom we got a another aldehydic molecule, and from this moiety we got a formic acid. So the product as like this, the formic acid comes from this, and remaining this moiety you can write as like this converted, this carbon is a converted to this aldehyde, and this converted to this another aldehyde, and after the hydrolysis we got the diglyceraldehyde as a product. When it is a 6 member ring, the product is diglyceraldehyde, and when a sugar is a 5 member sugar, then there is this OH and this OH, therefore breakage of this bond. Here again two OH groups, therefore breakage of this bond when it is reacted to the HiO4. That means here it is a CH2OH is attached to one more OH, therefore in the product after the breaking of this bond, from this we get the CH2 attached to the two OH group, this carbon attached to two OH group, and after the removal of we got formaldehyde as a product. From this we got the formaldehyde and another moiety as like this. Okay, so after the breaking of this, here we got aldehyde, here we got one more aldehyde. So you can write the structure as like this, and this formaldehyde molecule is come from this CH2OH. When it is reacted, this sugar is reacted with the two equivalents of HiO4, and after the hydrolysis we got a product which is different from this D-glyceraldehyde. So the 6-member sugar gives different product and the 5-member sugar gives different product. Therefore, from this you can determine the size of this carbohydrate. So this is the method for the determination of carbohydrate. So the another interesting topic is a disaccharide. So disaccharide is a type of a carbohydrate. So what are the disaccharide? So the disaccharide are the two sugar unit attached in this disaccharide. So these two sugar units are coming from the monosaccharide. So the monosaccharide is a single sugar unit which cannot be hydrolyzed. For example, the glucose and fructose. As we know, the glucose and fructose are the monosaccharide. Okay, this is the single sugar, okay, which cannot be hydrolyzed. And when these two monosaccharide are linked, then it is converted into the disaccharide. That means the disaccharide contain the two sugar unit. Okay, so how it can form? If the glycoside or acetal is formed by the reaction of anomeric carbon of monosaccharide with OH group of another monosaccharide molecule, then the glycoside product is a disaccharide. That means the disaccharide are formed when two monosaccharide units are joined. So how it can be joined? The first anomeric carbon of first monosaccharide. Okay, that means the anomeric carbon of first monosaccharide is joined to the OH group of another monosaccharide molecule when these two monosaccharide are linked via this glycosidic bond. This product is called a glycoside, and this glycoside product is called as a disaccharide. So you can see the reaction. This is the first monosaccharide unit. Okay, this is the glucose, and this is the another monosaccharide. Here we only concern with this OH group, therefore we cannot write the structure. Here I write only the R group. Okay, when the anomeric carbon is reacted with this OH group of second monosaccharide, the formed product is called a glycoside. Okay, so this product is a glycoside, and this glycoside, it is a disaccharide. So you can see here, this is the first monosaccharide, this is the second monosaccharide, and this anomeric carbon is attached to this second monosaccharide, and the product is called a disaccharide. Okay, so here you can see this is the first monosaccharide, this is the second monosaccharide, and the first anomeric carbon of first monosaccharide is joined to the OH of second monosaccharide. So you can see here there are 5 OH group. This 1, 2, 3, 4, 5 OH group. So from this sugar, any one OH can attach to this anomeric carbon, whether it is this OH, this OH, or this OH, or this OH. So from that we can categorize the disaccharide molecules. So in this reaction you can see the product. This is the first monosaccharide, this sugar first monosaccharide, and the anomeric carbon is attached to the OH of this second monosaccharide. So this OH is reacted with this anomeric carbon, and we got this as a product. This is the disaccharide, and this bond is called a glycosidic bond. Okay, so this is called the disaccharide. We can write the structure as like this, and here you can see this OH is a beta OH because it is equatorial, and in the product the stereochemistry of this OH is a beta. Therefore you can write here the beta glycoside. Okay, this bond is called a glycosidic bond, and this is the disaccharide. That means what are the disaccharide? Disaccharide is is a molecule in which the two sugar units are attached. That is called the disaccharide, or you can also call it as a glycoside, and this bond is called a glycosidic bond. So the anomeric carbon can react with any of the hydroxyl group of the another monosaccharide unit to form the disaccharide. That means the any of hydroxyl group from the second monosaccharide can be attached to the anomeric carbon of first monosaccharide, and from that we can categorize the position of hydroxyl group of the another monosaccharide which form in the glycoside. That means the disaccharide can be categorized by the position of hydroxyl group of another monosaccharide making up the glycoside. So the disaccharides have three naturally occurring glycosidic linkage. So the first link is a 1,4 link. The anomeric carbon is bonded to the oxygen on C4 of the second monosaccharide. That means this in the 1,4 linkage, the 1 is come from the first monosaccharide. That means this 1 is the anomeric carbon of first monosaccharide, and this 4 is a hydroxyl group of the or a number of carbon of the second monosaccharide. That means the anomeric carbon is bonded to the oxygen of C4 of the second monosaccharide. So this is called the 1,4 linkage. When the anomeric carbon is bonded to the oxygen of C6 carbon of a or a C6OH of second monosaccharide, then the linkage is 1,6 linkage. When the anomeric carbon of the two monosaccharide units are bonded through the oxygen, then it is called the 1,2 linkage, and the prime subscript indicates that the OH bonded carbon position of the second monosaccharide unit. The alpha and beta configuration given by the based on the configuration of anomeric carbon of the first monosaccharide. That means this prime subscript indicates the OH of the second monosaccharide units, and the alpha and beta configuration is coming from the first monosaccharide unit. That means if the first monosaccharide is present in the alpha position, then the linkage is alpha linkage. If the first monosaccharide present at a equatorial or a beta position, then the configuration is or the linkage is beta linkage. So you can see the first one is a 1,4 glycosidic linkage or a 1,4 glycoside. This represents the most commonly naturally occurring disaccharide. The linkage is between C1 of one sugar subunit and C4 of the other. That means the anomeric carbon of first monosaccharide is a C1, okay, and the OH or a hydroxyl group of C4 carbon of the another sugar, then the linkage is C4 glycoside. For example, the maltose sugar. The maltose is a disaccharide and it is coming or it can be formed when the two D-glucose units are joined via the glycosidic linkage. That two D-glucose units bearing 1,4 glycosidic linkage, and the stereochemistry of the linkage is alpha because the D-glucose is present in the alpha position. So the glycosidic linkage is called alpha 1,4 glycosidic linkage. So you can see the structure for the maltose. Here this is the maltose sugar and this is the disaccharide. So you can see the first monosaccharide, here it is a D-glucose, and here you can see this is the axial OH. The first anomeric carbon or first OH of this sugar is a axial, or you can write here as a alpha position. Therefore this linkage is alpha 1,4 linkage. The first D-glucose, this is the second D-glucose. The stereochemistry of the second D-glucose here it cannot be specified, okay. Just you can see the fourth number carbon hydroxyl group of fourth carbon atom is attached to this anomeric carbon. Therefore, and the anomeric carbon is in a this OH, this O in a axial. Therefore, you can write here the alpha 1,4 glycosidic linkage. So this bond is called a glycosidic bond, and this is the alpha position. Therefore, we write here it is a alpha 1,4 linkage. So this is the structure for maltose, and this is the disaccharide which is 1,4 glucoside or 1,4 glycoside. The another glycoside is a cellubiose, also contain the 2D-glucose subunit. That means in a maltose sugar there are also 2 glucose units, and in a cellubiose there are also the 2D-glucose subunit. Only the difference, in a maltose there is a alpha, but in a cellubiose this is the beta 1,4 glycosidic linkage. This is only the difference in the alpha and beta. Okay, so see here, this is the first monosaccharide, that is the D-glucose, which is present in the beta position, and this is the second monosaccharide which is also the D-glucose. That means when two D-glucose units are linked via the glycosidic linkage, we got the two product. In the first, if it is a present in the alpha, then this is called as a maltose sugar. If this first monosaccharide present in the beta position, then this is called as a cellubiose. So this structure is called as a, this is the structure for cellubiose, and the linkage is beta 1,4 glycosidic linkage. This is present in the beta position. This first anomeric carbon of first glucose, this is the fourth OH is attached to this anomeric carbon. Therefore, the linkage is beta 1,4 linkage, and this is the structure for cellubiose. The third disaccharide is a lactose, a disaccharide present in a milk containing D-galactose. D-galactose is a non-reducing sugar and the D-glucose is a reducing sugar. So, the lactose can be formed from the two monosaccharide, and the two monosaccharides are D-galactose and the D-glucose monosaccharide unit. So, these units are hooked together by a beta 1,4 glycosidic linkage. So you can see here, this is the beta 1,4 glycosidic linkage. So why it called beta? Because this is the first monosaccharide unit, and in the first monosaccharide unit, this carbon atom or anomeric carbon, this OH is a equatorial. Therefore, this is the beta position, and this is the structure for the galactose. This is the D-galactose, and this sugar is a D-glucose. And when this D-galactose and the D-glucose are linked via the 1,4 glycosidic bond, this disaccharide is called as a lactose. Okay, and this linkage is a beta 1,4 linkage. This is the lactose disaccharide. The next one is a 1,6 glycoside. The anomeric carbon of one unit hooked by the oxygen of terminal carbon, that is the C6 of the another monosaccharide unit. For example, the gentiobiose is a sugar with the two glucose units joined by the beta 1,6 glucosidic linkage. That means the name itself suggests the OH of the sixth carbon of the second monosaccharide, and here the first, it is a anomeric carbon of first sugar unit, and the linkage is called the 1,6 glucosidic unit. For example, the gentiobiose is a sugar with the two glucose unit joined by the beta 1,6 glucosidic linkage. So you can see the structure. This is the structure for gentiobiose. Here it is a first sugar unit. This is the glucose molecule. Okay, and this glucose is present in the beta position. This is equatorial. That means this is the beta D-glucose. Okay, and this is the another glucose molecule, but the OH is attached to this anomeric carbon is a sixth carbon atom containing OH group. Okay, so therefore the linkage is beta 1,6 glucosidic linkage. So this is the another type of the linkage. This is the 1,6 glucosidic linkage, and the structure is called the gentiobiose. This is the another one example of a disaccharide that called the gentiobiose, and the linkage is beta 1,6 linkage. The next one is a 1,2 glycosides. The glycosidic bond is hooked between the two anomeric carbon of a monosaccharide unit. For example, the sucrose contain D-glucose subunit and the D-fructose subunit, which have been joined by a glycosidic bond between C1 of glucose in the alpha position and C2 of fructose in a beta position. Okay, so these glycoside is a sucrose, and sucrose is come or a form when the D-glucose and the D-fructose are joined via the 1,2 glycosidic linkage. So you can see here, this is the D-glucose which is present in the alpha position, okay, and this is the fructose 5-member sugar which is present in the beta position, and this linkage is 1,2 glycosidic linkage, okay, and this form disaccharide is called a sucrose. So this is the 1,2 glycoside. I hope you understand. Thank you so much for watching.